So this is the last type of ICE table problem that you're going to see. And again, it's not different from the other ICE tables we've done. But when you get to the end, you're going to have a little bit of weird algebra going on. So you're going to need to be using the quadratic equation to help you solve for concentrations of things at equilibrium. So let's just go through this and I'll kind of show you what we mean when we get there. So I have to draw my own table here. So I have N2 as my first reactant. I have O2 as my second reactant. And I have 2NO as my product. And we're going to spell out ICE. Okay, so they're giving us the value of the equilibrium constant. So basically, like, we're going to have to figure out what the concentrations of everything is once we get there. So let's see, they're telling us we're in a 1 liter container, right? So even though they're only giving us moles of N2 and O2, I know moles divided by liters is molarity. So if I divide both of those numbers by 1, I get 0.2 as my molarity of N2 and 0.15 as my molarity of O2. So that's nice and easy. And just like every other problem we've done, we always start off with no products because we didn't make them yet. Now my change, my reactants are going to go down. My products are going to go up because there's 2 moles of N2. They're going to go up by 2x instead of just x, okay? And then at equilibrium, you take your I and your C and you smush them together. So at equilibrium, the concentration of N2 will be 0.2 minus x. Oxygen will be 0.15 minus x. And NO will be 2x. Okay, so if I take now my equilibrium constant and I write it out, I have my products over my reactants. They gave me the KEQ of 4.1 times 10 to the negative 4. They gave that to me in the question. For the concentrations, all I have to plug in are what I solved for in the E row. So NO is 2x, and that's squared. And then I have N2 is 0.2 minus x, and 0.15 minus x. Okay, so now I have a big mess here because I can't just take the square root of this whole right side like I did before because my denominator isn't something that's squared. It's 2 different values. So I'm going to have to just kind of work that out, simplify what I can. 2x squared is 4x squared. And if I multiply these equations on the bottom here, I get x squared minus 0.35x plus 0.3. Okay, so this is looking like it's going to be messy. If I put this over 1, I can actually cross multiply. So 4x squared times 1 is 4x squared. Now this 4.1 times 10 to the negative 4 is going to have to get distributed to every term in this big long thing down here. Okay, so this is going to just take a little bit of time. You guys should kind of maybe be pausing the video and seeing if you get the same thing as me when you distribute. Ugh, what a mess. Alright, now if I take this 4x squared and minus it from this side, and minus it from this side, because I have x squared here, I actually can set this whole thing equal to 0. So we have 0.99x squared minus 0.000143.5x plus 0.000123. Okay. So now I'm at a point where I can solve for x, and to solve for x we need to use the quadratic equation. So I'm going to write the quadratic equation over here. X equals okay. So basically, you're going to take this number and plug it in for A. Whatever the x squared is attached to is your A. Whatever the x is attached to is your B. And whatever your only number there is your C. So I'm going to take all those numbers and plug them into that equation. And I'm going to get two answers for x. Okay, and guys, you want to just kind of like use your common sense here. X is a concentration, so you never want to choose a negative value because you can't have a negative amount of something. So for this problem, I'm going to choose to plug in 0.0017 for x. Okay, you want to think like whatever you started with on your reactant side, you're always turning. Actually, I don't want to say that. Never mind. Let's just go with that. Okay, so now I have this value to plug in for all of my things. So I have O2. I'm just copying this from like 3 slides ago, guys, so that you can all see it. 0.15 minus x, and I have my NO, which equals 2x. So I take 0.0017 and I plug it in for x for all these spots. I get the molarity for all of my reactants and products when we're at equilibrium. Okay? Now, you're going to kill me because, well, let's stop there for a second. I want you guys to actually pause this, and I want you to look at page 6 of your worksheet packet, number 45. That's a problem that you have to use the ICE table and the quadratic equation to do. Do that problem, check the answer key, and then come back to this video where we're going to look at this little cheat sheet. Okay? Assuming that you guys went and did that. Okay? So there's something that you can actually do to avoid using the quadratic equation. When they give you the KEQ, which they did in that problem, if the KEQ is less than 1 times 10 to the negative 4, that means that not enough reactants turned into products that, like on the reactant side where we wrote the change, the minus x, it means you can completely ignore that as if that change didn't even happen because so few reactants turned into products that it's not even worth counting. So then what would be my concentrations for N2 and O2? They would just be 0.2 and 0.15 even at equilibrium. So let's look at how that's going to simplify everything. So I ended up, here I drew my ICE table, I ended up having this. And you guys wrote this down up there. So if you're not sure where I am, you can scroll up and look. But we got to the point where we had this, and we had to solve for x. So we started cross multiplying and all that stuff. If this minus x is not there, now I just have a denominator that doesn't have an x in it. 4x squared over 0.2 times 0.15. So we don't have to worry about using the quadratic equation. So that's nice and easy. Alright, last thing, guys, we're going to talk about manipulating equations and figuring out KEQ. So this is kind of like shortcuts of figuring out what a KEQ is so that you don't have to use any math. So here, let's say here's my equation, right? Going forward, I have synthesis, and going in reverse, I have decomposition. And I'm just going to make up a number here for simplicity. Let's say that the KEQ of this equation is equal to 10. Okay? Now, what did we do here? We took the reaction and we wrote it in reverse. So if you know what the full reaction is, if you take that reaction and put it in reverse, the KEQ is just the reciprocal of that. So the reciprocal would be 1 over 10, which would be 0.1. So I just can say, okay, do the reciprocal, that's the KEQ. I don't have to do any ICE tables or anything like that. Let's look at this last one on the bottom, guys. How did that change? We took everything and we doubled it. the concentrations, we doubled the number of moles. So if you double your coefficients, you need to square your KEQ. So if the KEQ was 10 and now I squared it, the new KEQ is going to equal 100. So if you guys want to do practice on this, you can do page 3 of the worksheet packet. Oh, and I should have mentioned up here, one of the questions on page 6 of the worksheet packet, it appears as if you have to do the quadratic equation, but the KEQ that they give you is actually very small, and you can use this cheat sheet method. So if you're looking for another example like that, you can also do page 6, number 46 in the worksheet packet. All right, so that's it for now, and I'll talk to you guys soon.